Now we are going to start with colligative property. Right. So first of all, you should know that what is colligative property. In order to make you understand, I am just taking an example to make you understand in a better way that what actually is a colligative property. Look at the board carefully. See, I have this container in which I have a pure solvent. And let me mention that this solvent is volatile. So that means it will exert a pressure. Let us say that the pressure equals to let's say P naught A. Now I have a solute. So let it be my solute as B, right. So it will also exert certain pressure, let's say P naught B. Now when I am going to mix them in a beaker, so that means I am going to make a solution. So there what I will get to see that there might exist the vapor of solvent or a solute, or the number of vapors which exist above the surface of the liquid may vary. So that means accordingly the vapor pressure may increase or decrease depending upon the you can say the nature of the solute and the solvent, or depending upon their tendency to escape, right. So that means vapor pressure may increase, vapor pressure may decrease. That depends upon what factor it depends. Obviously it depends upon the number of solute particles. And one more thing, it depends upon the attractive forces also. It depends upon the attractive or the binding forces that exist between the particles. Right. So that means when we are mixing the solution, when we are making the solution, or you can say when we are mixing solute and solvent, vapor pressure may increase or vapor pressure may fall. It just depends upon the number of the solute particles. I think it's clear that it depends upon the number of the solute particles, because it depends that actually that how many of the solute particles are causing a hindrance to the solvent particles to get evaporated, or likewise that means the vapor pressure may increase or decrease accordingly. So that means here the vapor pressure, the falling of the vapor pressure or rising of the vapor pressure just depend upon the number of the solute particles and also on the binding forces. As I told you in a previous lecture that when the binding forces are less, so that means the escaping tendency will increase, and when the binding forces are going to more, the escaping tendency is going to increase, right. So that means it doesn't depend upon the identity, does it? No. Suppose I take you can say I take 1 kg of water and I am adding 1 mole of NaCl into it, and likewise I am taking 1 kg of water, I am adding 1 mole of urea to it. You will see that the vapor pressure increase or decrease in the same way, irrespective that whether you add NaCl or urea, the fall or increase in the vapor pressure is just going to remain same. So that means all those properties which depends upon the number of the solute particles present in a solution and is independent of their identity, those properties are something called as colligative properties. I repeat, just write in your copies. Colligative properties are those properties which depend upon the number of solute particles in the solution, right, or you can say the binding forces that exist between them. So we take into consideration only these two criteria, but it is actually independent of the nature of the solute or the solvent, or you can say it depends upon the nature, it is independent of the identity, that whether you are using NaCl or whether you are using potassium iodide or whether you are using urea, it doesn't make a difference. It just depends upon the number of solute particles which are present. So this is what is the colligative property. We get to see many colligative properties because I have 4 colligative properties, because you have 4 important colligative properties in your syllabus, that is relative lowering in vapor pressure, elevation in boiling point, depression in freezing point, and osmosis. Relative lowering in vapor pressure, I think it is clear from the name that the vapor pressure is something getting lowered, right. Elevation in boiling point means the boiling point is rising up from the normal level. Depression in freezing point means the freezing point is falling, and osmosis we will be discussing. As you all know that osmosis is a movement of solvent particles from higher concentration to the lower concentration. Now we will be taking into consideration all those 4 properties, and I will just make you realize that yes, they are a colligative property. They depend upon the number of solute and irrespective of the identity of the solute. So just look at the board carefully. So we are starting with the first property, let us say relative lowering in vapor pressure. Relative lowering in vapor pressure. Now suppose I have a solvent. See, whenever you explain these kind of questions, just make use of figures. More you will make use of figure, more you will be clear in answering, right? So just look at the board. Suppose I have this solvent, let my solvent be A. I specify you that my solvent is volatile. Volatile means, that means it has an escaping tendency and it is going to form vapors. So let these exist as my vapors of this pure solvent. Let the mole fraction of the solvent be XA and the partial pressure which it would exert alone, let it be P naught A. Right. Now I have a solute in another beaker, and let me tell you, this time my solute is non-volatile. It is not going to form any kind of vapors. As the non-volatile, they don't have the escaping tendency, right? So this is my non-volatile solute. Let its mole fraction be XB. Right, and because I am considering solute as B, and as I told you, it is non-volatile, so none of the vapor will be found, right? So that means there won't exist the partial pressure, or you can say P naught B is definitely going to be 0. Now I am going to mix them up in order to make solution. So now in my solution, what do I have? I have a solvent which is volatile, that means has an escaping tendency, and I have a solute. Let me make solute with red. I have the solute which are non-volatile, that means they don't have escaping tendency. So in this kind of solution, will I get to see vapors? Yes, definitely I am going to get vapors, but in this case vapors are just going to be the vapors of the solvent, because you can say because the solvent is volatile and solute is non-volatile. So the total pressure which it would exert, as we know, otherwise equal to P1 plus P2, that means the pressure of solute plus pressure of solvent, but in this case the solute is non-volatile, that means I have to neglect this pressure. So my total pressure depends upon only the one factor, that is the volatile factor, volatile component, that is the P1. And as I know that P1 is something equal to P1 naught into X1, so that means my total pressure is this, right? Now as you all know that for a binary solution, our sum of mole fraction of two component is equal to 1. Keep in mind, because I will be using this now. So let us see that how the lowering of vapor pressure can be expressed mathematically. It's clear theoretically that why the vapor pressure is getting lowered, because due to the solute nature, because solute is non-volatile in nature, it will occupy some of the surface and won't let the solvent molecules to get escape. They won't be letting it to make the vapors. So that means the vapor pressure is somehow going to be less than the vapor pressure it would exert when it is present in a pure solvent form. Right. So that means I can write that if I want to see the change in pressure, so obviously as I told you that the pressure due to pure solvent is going to be more than the pressure it would exert when it is present alone. Right. So that means we have to subtract, or we can subtract this PA from P naught A, because P naught A is greater, right? In this case the pressure it is exerting when it is present alone as a solvent is more as compared to the pressure when it is which it is exerting when it is present in a solution form. So I can write this in this way also, that it is equal to, let me put this value, substitute its value, so it is to explain. Whether you take P1 or you take PA hardly matters, right? A means to the first one and the first means the first one, that is our solvent, right? So I have this. So I can write this as this also, that P naught A minus P naught A. I am going to put this value in terms of XP. So what I have, 1 minus XP. Likewise, as I told you, X1 plus X2, we can have XA plus XB is equal to 1. So I am taking the mole fraction of XA in terms of XP. So what do I get? I get 1 minus XP. Let me solve this equation. So what do I get? I have to multiply it in order to open the bracket. Now further simplifying, cancel this. So that means delta P is equal to P naught A into XP. Right. I can write this as this also, that my delta P, that is my change in pressure divided by my pressure of the pure solvent, is equal to its mole fraction. I can even write the value for delta P. Delta P is something this. That means P naught A minus PA divided by P naught A is equal to XP. Now, as you know that this expression is actually lowering in vapor pressure, because this shows that the vapor pressure of the pure solvent is more and the vapor pressure which it is exerting when it is present in a solution form is less. So that means this indicates the lowering in vapor pressure. And when I take a ratio for P naught with the P naught A, it becomes relative lowering in vapor pressure. Now, can you tell me that is it a colligative property? Is it proved? Yes, it is proved, because you can say that relative lowering in vapor pressure is something equal to the mole fraction of the B, that is our solute. And as I told you that colligative properties are those which depends upon the number of the solute particles. So it is now depending upon the mole fraction, that means it is depending upon the number of moles of the solute and independent of its identity. Right. So this is what is the relative lowering in vapor pressure. This expression as actually this expression can also be used to found the molar mass also. Just look at the board how it can be used. See, I'll write here. So this indicates that P naught A minus PA upon P naught A, that is relative lowering, is equal to XP. And we know that mole fraction is nothing but moles of B divided by total number of moles. That is the moles of A and B. Now we know that moles are indicated by, like I have to find for B, so that is weight of B by molar mass of B. So that means by putting this value I can have this WB upon MB divided by WA upon MA plus WB upon MB. As you can see that the concentration of the solute is very less in the vapor phase, because it is almost non-volatile. That means it is very less. So that means in case of dilute solutions we can just neglect the moles of the solute. So this is what I am going to do here. I am just going to neglect this factor. So what I will get by neglecting it, P naught A is equal to WB upon MB into MA upon WB. So by using this formula we can calculate the molar mass for this solute. So it becomes MB is equal to, this is A. MB is equal to WB into MA divided by WA into relative lowering in vapor pressure. That is our expression. So by this formula, if we need, like if somebody asks us to calculate the molar mass, like rest of the things are given and you need to find the molar mass and even the relative lowering is given. So in that case you can use this formula. Otherwise if somebody is going to ask you about relative lowering, you just have to answer that how and when the relative lowering take place, or what kind of mathematical expression you can use to just explain that property. So this is what is the relative lowering of the vapor pressure.